Welcome to the Semi-Conscious podcast from TKO, the specialist marketing services agency for the electronics industry. I'm Tim Weeks, a writer and marketing consultant at TKO. Today I'm delighted to be joined by Riccardo Collura of Future Electronics to talk about the use of wide bandgap materials in silicon carbide and gallium nitride in power electronics. Riccardo has an excellent view of the power electronics and power component markets through his role in charge of European power electronics business at Future Electronics. More important, Riccardo is one of Europe's most knowledgeable voices on power electronics, thanks to his career as a power specialist engineer at TDK Lambda and XP Power before he joined Future Electronics in 2017. Riccardo's specialization in power electronics stretches all the way back to university in Palermo, where he took a Master of Science degree in electronics engineering. I started by asking Riccardo about what are the special features of silicon carbide and gallium nitride that make them so appropriate for use in power electronics designs.
Wide bandgap is something that we have been talking about ages, decades for sure. Since I joined the power electronic industry back in 2010, there was already talking about silicon carbide and GaN, the two main material for wide bandgap that are used for power electronics.
Yeah.
What is special with that? Finally, I can say now that we are able to use the best of this material on power electronics, because as I said, back in 2010 we knew the potential, but we didn't have a way to optimize the use of these technologies. So basically it's all referred to the bandgap of this semiconductor material, which is much larger than the classic silicon-based system. So what does it mean? That you need more energy to free electrons, and that give this material a special characteristics like high voltage breakdown or better thermal conductivity. So basically, we have materials, SiC and GaN, which are not the same, by the way, that can make your system switching much faster. You increase the power efficiency, and you can really have a high power density power supply.
Absolutely. And is there anything also about sort of the thermal characteristics of these materials that's significant?
Yeah, as I said, especially for silicon carbide, this is true. It's got much higher thermal conductivity. That means that this material can work at much higher temperature than silicon. So that means that power electronics, when they run 24 hours, they get hot and hot. So you basically you have two advantages. They can work at much higher temperature, but on the same time, because you are still limited by the PCB, basically you reduce your thermal heatsink. So you can have a lighter system. So because they can work at much higher temperature, you don't need a massive heatsink like you need for classic silicon, but you can reduce the heatsink, so you can have a much better thermal management in your power system.
Okay, so that elimination of or the requirement for a smaller heatsink or smaller thermal dissipation device. So that's part of the reason why we're able to create power electronic systems that are smaller. But there's also the faster switching also plays its part.
That's the other big advantages. Basically, because of the characteristics, you can switch a much higher frequency. So they can work at fast switching. So basically, the advantage is translated also on the passive that you use. All your resistors, capacitors, the magnetics, they can be smaller because they can work on much higher switching frequency. Overall, ultimately, you can get a smaller, higher power density, so a smaller system with the same power level, basically.
Yeah, and
that's true. That's true for silicon carbide and GaN, of course.
Yeah, absolutely. Yeah, just to give us a little bit of this of the scale of this. How much of a smaller system is you're able to produce?
Yeah, so let's say for just to give an example, let's say you have a 5 kilowatt system, and you have the silicon base and the silicon carbide base. So either you can have the same power level, and probably you reduce almost by half the size of your system. Okay,
much, right.
maybe a bit more, but half is a good number. Or with the same size, you can achieve double the power, so you can have a 10 kilowatts. So just to give you a figure on the potential of silicon carbide and GaN. As if you think of GaN, which is mainly used on laptop, tablet, mobile phone. You can really go even higher in frequency. You can do very flat design. You can get the high efficiency, small design. If you think all the chargers now for iPhone and smartphone, they are very compact, but they are like 60 watt. So you have in a small square, you have 60 watt of power capability.
So, given this very, very substantial advantages that you're describing, the massively increased power density, the higher thermal headroom that you've got, given these huge advantages, what is it about these materials or about the devices based on SiC or GaN? What is it that means that there's still a huge amount of power electronics design being done with silicon devices rather than wide bandgap?
Yeah, so that mainly is, engineers are always they feel more comfortable in this if they stay in the comfortable area, right, zone.
Yep.
So they always been designed with IGBTs, with silicon MOSFET. They've got something that is working fine, with a decent cost, low cost. So the transition to a new technology, which is a lot more expensive, of course, is a bit like scary sometimes. However, and this is to connect with what I said before, because especially the automotive market is driving the demand. So all the suppliers, the big suppliers, are investing hugely on silicon carbide and GaN. That means that the price is going down. And one of the key, our responsibility as a distributor like Future is to educate the customer and to try them to think about the system cost and not just comparing silicon versus silicon carbide, for instance, because silicon carbide will always be more expensive than silicon. I mean, it won't be any time that the silicon carbide will cost with similar DSO and so on, like the silicon. But
today that difference is what 2 times, 3 times, 4 times, 5 times.
It used to be like 3-4 times 2-3 years ago. Now I think is probably 2 times, maybe for some cases even less than that. But the cost that you save in other part of your system, like we discussed before, the passive components, the magnetics, the thermal heat sinking. So at the end, for some applications, we know already it's demonstrated that the system cost is maybe lower if with silicon carbide, and you get much higher performances.
Yes.
So and the other thing also for a customer to be a bit reluctant to use, it was for sure the supply chain, the demand. A lot of suppliers, they were driven by their OEM customers. So that means that there was no capacity for all the mass market. But now with the huge investment that they having to increase the capability and the capacity, and we see press release from our suppliers pretty much every day. Now, every customer has access to these technologies. So it's just now a question of when to use it, not if they can use it.
Yeah, absolutely. So if I were a power system designer, I'd be thinking, well, it sounds like it's a bit of a no-brainer. I've got to move to wide bandgap. Is there still something beyond that that's got to do with actually these wide bandgap devices are a little bit more difficult to work with than silicon MOSFETs or IGBTs that designers will have been used to working with?
So, I mean, we don't have to think that we have a silicon-based system. We drop a silicon carbide with the same package, and it's gonna work. It's not like that. Different device, different technology will require also a different layout, different gate drivers, which is key, especially for for silicon carbide and GaN. They are not. You don't drive a silicon carbide as you drive a silicon MOSFET or IGBT, and the same apply with GaN. So it's clear that it requires expertise. It's not just a drop-in replacement. Some people thought that was easy like that. It's not like that. So there is a lot of attention that a customer needs to be paid when they do layout, because the leakage inductance, and that's also the reason why for these devices, GaN and SiC, you need, let's say, the optimized package is not the same of the silicon. So you see now a lot of supplier developing a topside cooling package, for instance, or for GaN is SMD. So you have a very flat package SMD. So you don't see like TO220 GaN. I mean, there are in the market, but now the trend is to go SMD, and this is just because finally we have the maturity to understand that we don't have to treat those new material as we have done in the past with silicon. So optimized package, different way to drive, and pay extra attention to layout. We can design, we have some design with wide bandgap, so we have the expertise, and this is all about sharing the knowledge, the tips and tricks when it comes to the use of wide bandgap. We have also bad experience when people, as I said before, they thought that silicon carbide was a drop-in replacement, and this happened with a motor drive customer. And maybe then we can touch also on the applications where silicon carbide is a must and where we are in the transition. Motor drive is one of those applications where we are in the transition period. So we have conservative engineers. They stay with IGBT. It works. They're cheap. No way they change. Even they are thinking about. And we have other engineers, maybe a bit younger. They want to use new technology, but they don't have the expertise. So what happened at this customer? We talk about silicon carbide. They wanted to test, and they just took out the IGBT, put the silicon carbide, switch on, blowing up. Of course, it's not like that, as I said. So they need to redesign the PCB. They need to use different drivers. They need to read the data sheet very carefully, because there are some silicon carbide that you need negative voltage to be driven, and other silicon carbide that you don't need that negative voltage. So definitely there are a lot of part around the silicon carbide that needs extra attention. So this customer was a bit scary. So okay, this time I'm going to use the IGBT, but still we are teaching them somehow in how to use the silicon carbide, maybe in the next design, in the fresh new design.
Absolutely, yeah. So it's very obvious that there are always ways that this can go wrong. There are mistakes that you can make that you need to avoid, and absolutely.
Yeah, okay. And this is happened also with GaN. GaN is very difficult to drive. It's very sensitive. If you get high voltage in the gate, once you damage the GaN FET. So that's why the trend is to integrate the drivers with the FET. That will easier the design for engineers. So we see ST, Power Integrations, MPS, Infineon, all of them, they've got solution with integrated driver with GaN, just to try to not having problem externally when you have to drive GaN and so on.
Absolutely. So you can use an external driver with a GaN.
I mean, we have both options. We have discrete GaN, and you have integrated driver with GaN, and also you have in the discrete you have two different. You have cascade, which means that you have a low voltage FET integrated. So basically, you are going to drive that low voltage FET. So let's say it's a bit easier to design, but somehow you lose a bit of properties of the GaN. So you're not going to, you will add some capacitance, some parasitic, so you don't get 100% of the benefit, but you have easy drive. And then you have the normally off devices, so the HEMT devices, where they are, they require a special driver, so a dedicated driver for GaN. I think one thing to highlight is that maybe even 10 years ago, there was no clear difference between GaN and SiC. So we were talking about wide bandgap, and some people thought that was similar devices. Well, it's not like that. I mean, silicon carbide and GaN are targeting different market. Yes, there is an overlap, and the overlap is in the power level of 3 kilowatt, where silicon carbide and GaN, they are giving similar performances, so that we will know in a few years who is going to take the main share for that power level, mainly for industrial power supply. But of course, silicon carbide is targeting much higher voltage, higher power applications, EV charging, energy storage, industrial motor drive, welding machine, and so on, while GaN are targeting the low mid power, so USB Type-C chargers, battery chargers up to 400 watt, e-bike chargers, and then, as we said before, laptop, tablet, mobile phone. Don't get me wrong, silicon is not going to disappear. It's not that we have alternative, that silicon will stay there. It's still strong market, and there will be applications where it still makes sense to use silicon as per today. So the IGBTs, the superjunction MOSFET will stay there, so we can reassure everybody that it's not something, we just different applications.
Just casting our eyes sort of into the future, is the main development that you expect to see is continued investment in capacity leading to continued drops in unit costs? Is that sort of the main thing we should be looking at over the next 2 or 3 years?
I mean, we know, I think it was only a couple of days ago, we done Semi that they have the new factory in Asia, in Infineon investing billion. ST, they're building a new factory not far from where I live in Sicily, in Catania. So yes, it's all about because the demand it will only grow. If you think both automotive and industrial market will only grow. So definitely, I also would like to highlight the importance of the smaller companies, where sometimes the major suppliers, they are fully booked, or they cannot deliver even if they're increasing the capacity. So it's important to have a lot of alternative thinking. Company like MCC, SMC diodes, for instance, they are new in the market, but definitely Vishay, Diode Sync, all these let's say new players will help in trying to fill the gap in capacity. That's for sure.
Is that giving customers just greater choice?
Just to fill the demand. So when I joined the company, Future Electronics, back in 2017, we have probably maybe 2 or 3 suppliers for silicon carbide. Now, if you look at our line card, we have probably 12, 13 different suppliers for silicon carbide, and we know that more will come in the next few months. So it's all about fill the demand with the investment. So customer, they're sure if they are not getting the part from X suppliers, they will get the part from another suppliers.
Absolutely. Okay. All right. And so we've sort of talked a bit about the magic of silicon carbide and gallium nitride, these sort of amazing materials that produce these devices that are in some ways so much superior to silicon. Is there any other magic out there that's waiting to be sort of discovered or introduced?
So there are potential other wide bandgap material for sure. Just to name a couple, maybe the 2 actually which are more real. Diamond, for instance, which probably will be the ultimate wide bandgap semiconductors, and also gallium oxide there is some research around that. Very early stage. I know that there is already like a diamond FET prototype built up, but of course, as you can see, there is a lot of difficulties because it's a very hard material. So it's going to be even more difficult to work the diamond compared with silicon carbide. But of course, theoretically, potentially, it will be maybe a diamond could be for silicon carbide what silicon carbide is for silicon.
Wow.
So
Yeah. That amount of
that
improvement.
different.
Yeah.
But
Yeah.
maybe we will have an interview in 10 years, and
Yes.
then we will see update.
Indeed, yeah, but presumably it's pretty hard to form circuit structures in diamond when it's such a hard material. That
But
must be.
you know that the market nowadays is very fast. I mean, if you
Mm,
see silicon 60 years old, and it's been for 50 years, it was just silicon, silicon, silicon.
yeah,
And then
yeah,
in less than 10 years, we now see the ramp up of silicon carbide and GaN. So, of course,
mm,
we live in a very fast society. So the technology will move fast. So you never know what
and
happens.
absolutely.
We are here to see, and we are curious. I'm very happy to be part of this time frame.
It is. It's
To
it's a
see
very
to
it's very
see. Yeah,
exciting, isn't it? I mean, and what you were saying about sort of the movement in the market, the capacity and the reduction in unit prices and so on is. I mean, that's sort of very exciting um, for you and for I think everyone in the power electronics world because it makes these things so much more available and affordable. And
yeah, absolutely. And then there's the very good things to work for a distribution like Future. Just that we have this overview on what's going on, with our suppliers, so we can share, our knowledge and learning to our customers to help them.
Indeed, and thank you, Riccardo, for sharing your knowledge and learning with us today and with the Semi-Conscious podcast. I think it's been
My pleasure,
fascinating
Tim.
for our listeners to learn more and to benefit from your knowledge. So thank you very much for taking the time to talk to us.
Very welcome. It was my pleasure.
Okay, great, thank you.